squared underneath. Right? Okay. Now, so we've got the eigen. We've got the eigen values. Now, so we have an upper and lower limit on the power of the rho in the expansion, the weighted sum expansion of f, big F, right? We have a recursion relation between A of p plus 1 and its relation to A of p. So we know all the coefficients of A. We know all the A coefficients, and therefore we can find F, right? And remember we said before F is a polynomial. So for different p's, little p, we'll get different polynomials. And these polynomials, again a Frenchman, I guess the French were heavily into polynomials at the time, and this time these polynomials, these f's here, are called Lect polynomials, and I don't know if that's just coincidence, a bit of a joke. If you know any French, Lect means war, it's war, W-A-R. So Legt polynomials for f. And right, so we now know that these f's here are Legt polynomials. Now the textbook doesn't supply you any. What have we done? What polynomial types have we done already? We've done Legendre polynomials. How many different polynomials have we done? 2 or 3? Legendre, Legt now. Were there others? There's another one. I'm forgetting. We've done 2 or 3 French-named polynomial types already, right? Okay, so these f's will depend. You can see it here. These polynomials, coefficients, they will depend on L because you've got an integers p, of course. So these coefficients will depend on L. If the coefficients depend on L, then the polynomial f will depend on L and p. So this polynomial is a function, depends on two factors. N, that's your integer for the you plugged into the energy eigenvalues, and L. Alright? So we can rewrite this, the big R, in terms of these two parameters. Right? So N, L. Now remember R, we defined R, we split big R into a factor, 2 factors, one of R and the other F. I think that was an earlier session. Right? Okay, so bringing it all together now. So, oh, here it is. Yeah, here. Yeah. So we split R into this and some function of rho. Well, we now know that this F is a Legt war polynomial, right? Okay, and we know that R depends on N and L, so we can write it this way. And now we can write out the full wave function for the problem with a central polynomial. What time is it? It's about 6 p.m. I'm starting to fade. Yeah, starting to fade. So my brain is slowing down a bit. Okay, so these U's, they are the eigenfunctions of the general Schrödinger equation for the central potential. Okay, and in the general form, so they're a function of three parameters, r, theta and phi, so the spatial part and the, let's say, orbital part, the polar angle part, theta and phi. So this term here is just the normalization constant. Don't worry about it for the moment. It's just there such that the bracket gives you 1, so it's normalized. So it's just the normalization constant, hence the n. Now, this is your spatial part. Sorry, the orbital. How can I put it? The polar angle part. Let's say theta and phi, the spherical harmonics, and here's your spatial part, depending on position. So big R. So take the product, effectively these two. We made that assumption earlier, and so we take the product of the polar angle part and the radial part, the position R, okay, and multiply by a normalization constant, and you can then take the bracket of these, and the textbook hasn't done it. I haven't done it. It looks like hard work. I mean, look at this. Look at this. It looks quite complicated with factorials and so forth. So, if you like a challenge, have a crack at trying to derive this normalization constant that goes here. It looks to be non-trivial. Okay. Now the spherical harmonics are already polarized. Not polarized. Normalized. So we know that. Okay, now the next session, some actual examples, concrete examples of these for differing values of n, L, and m. We'll actually write out the actual expressions, the functions for we know what we've done. The spherical polynomials before. So you'll see familiar terms for the y, the spherical harmonics, in next session, and these will be Laguerre polynomials, and so the product. All right, and for various values of n and l, you'll get this stuff. All right, so. Now a bit of a comment, just to finish off this session. All this analysis we've done, effectively like just one electron with a central potential. But say you have, here's the critical word here, ion, an I-O-N, an ion. What is an ion? It's a charged atom. If you strip off one electron from the atom, then that leaves the atom positively charged, because in a neutrally charged atom there are as many electrons as there are protons in a nucleus, right? So the two charges cancel in a sense. Well, if you strip off one electron, that leaves one excess proton, so the atom is then has an excess positive charge. So positive or negatively charged atom is an ion. So if you add an extra electron to the atom, then that atom would become negatively charged because the excess one electron. Okay, so an ion. So if you have here like an ion of an atom with several electrons, and you strip away all the electrons except one. Okay, so if the nucleus of that ion, if its atomic number, in other words, number of protons, is Z, big Z, then the total charge of the nucleus will be ZE, right? But positive, where E is the absolute value of the charge on the electron. Okay, so so all this analysis applies also to the case of when you have an ion with one electron. All the other electrons have been stripped off. Then everything's the same, except your E here becomes well, E squared becomes Z E squared. And you can check this experimentally. And I suppose another quick comment. If your energy, your eigenvalues, I think we talked about this a bit before also, if the eigenvalues go positive, then there's no, there is not, right? The there is sign, I suppose you're familiar with it by now. I've talked about it quite a few times in lectures. So with a stroke through it, you interpret that to mean there is no, there is not, there does not exist. Okay, so there are no bound states, and the energy levels then are not quantized. They just can take continuous values, and then you get the classical mechanical type phenomena. So you just get the energy levels. They just form a continuum. Now we had something like that for the infinite square. No, the finite square well, I think. Right. Now, next session I will show you for the different values of n and l and m. I'll actually show you some of for the smaller values n, l and m, because believe me, as these numbers go up, this term here gets very complex. So just for smaller values, I'll actually show you some concrete examples of these general wave functions that are now functions of the angles and the position. Right? So we've made some real progress now. We're getting close to the real world in terms of the hydrogen atom, at least. And also, next session I will show you actual graphs. So you actually get pretty pictures. You actually see how these things look. At least in terms of R, the amplitudes, and then we can square them and get probability densities for R at least. Now we've done spherical harmonics, with all the wings coming up. So when you combine these two. You get quite a complex system. So I could. This is not in the text, just me saying. Just solving the simplest atom, quantum mechanically, the hydrogen atom, is, you can see, is getting increasingly complex. So solving multi-electron atoms gets very complex, and you're forced to go into numerical analysis. You just, in other words, you have to use a computer, because the formula get too complicated, and it becomes messy. It gets hard, because even the hydrogen, solving the hydrogen case quantum mechanically is not easy. Okay, so next I'll show you the pretty pictures and give you some of these eigenfunctions here, the U and Ln.